Hello, everyone. Welcome to this week's binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Today we have some bugs in cURL, a pretty insane heap overflow exploit with a custom TCP stack, and the Masticore follow-up with a PS2 emulator escape. And we'll get into all of that after Z gets into this week's Spot the Vuln, and I'll let him take that away.
And this week's Spot the Vuln is in something that you should never do in C, which is string parsing or processing. Honestly, just don't do it. There's so many ways this can go wrong. Like, that is very much like the first issue here is the fact they're even doing this in C. That said, the way the code ends up working here, it effectively starts off trying to parse out the username part of the email. So first bit until the at. Finds, wherever the ad is, tosses in a null byte, reads a link, make sure it's good before copying in that first part of the email. Then it looks at the remaining size after the at sign for the domain. And again, does the size check, making sure it's going to fit into the domain structure. And copies that in. And the problem is, if you do not include a dot in the domain, it's going to go ahead and have a default domain that it'll load in there for you and just copy in. So if you were to give it an email without a domain, it's just inserting like whatever the default like local network domain is, something like that. Is the ID here, so it has that default domain that's going to toss on, and it does that without doing any bounce check. So core issue here does bounce check everywhere except for that last one. Doesn't do the bounce check, so it could in theory overflow if you provided a domain that would just fit inside there, followed by the default domain. If you don't provide, if you give it a domain that does not have a dot within it, so it falls into this default case, it'll go ahead and toss the default domain on there without checking bounds and potentially overflowing.
All right, so we'll get into our topics. So up first, we have the cURL audit that was done by Trail of Bits. And this was a bit of a fun post. There was a bit of a joke aspect to it, as the headline implies. One of the team members at Trail of Bits was joking like, "Hey, let's pass. Has anyone tried curl?" And then a string of A's, your classic CTF payload. But that got them thinking, like, oh, what if we actually try to fuzz the curl command line interface? So that's what they started tunneling in on. They started researching into that, and they actually did find some vulnerabilities. And it's also a bit interesting because while they're fuzzing argv here, which you would think would be the most straightforward method of input, AFL doesn't actually support it officially outside of an experimental sample. So they had to figure that out and try to get a good harness working for the argv fuzzing. They also made a dictionary by using like AFL Clang L2's auto dictionary tool against the curl build, and also built a custom dictionary based on the man pages. But yeah, they did manage to get some findings. Unfortunately, they don't go super deep on them. They most of the things they found were use after freeze or double free. So yeah, like the first double free they found, uh, they found this one when they were using curl to proxy to dict Gopher, LDAP, or Telnet protocol. That triggered a double free, presumably similar to other cases we talked about, where some path frees the buffer, doesn't clear the reference, and then something else at a higher level sees that error and frees it again.
Yeah, with all
But
of these, we don't really get much information on how the vulnerabilities were caused. Just here's a crash,
yeah,
here's what happened, and the rebros.
Yeah, pretty much all of them though. It's hinted at that it's happening in the like error case, like edge case handling, which makes sense. For example, like another one was the UAF when trying to tunnel through an HTTP proxy, and if that proxy blocks SMB or Telnet protocols, you can trigger the vulnerability. And then another one with the parallel option by passing an unmatched bracket and passing two sequences that create 51 hosts. On that second sequence, when it hits an error to the unmatched bracket, it'll go to write that error into the buffer that was just freed when handling the first sequence. So yeah, it's kind of some low hanging fruit bugs in the error handling. It's not super surprising to see these kinds of bugs, especially in these weird edge cases that you think might not be easy to reach from command line. And to be fair, like the POCs here are like they're not super intuitive. Like root causing these bugs, you'd have to go and it wouldn't be like easy to spot the bugs probably. Um, but yeah, like the more interesting aspect is the argv fuzzing. I can't recall us ever covering a topic that really delved into that, because
No,
it's
and
just not a common interface to have access to as an attacker, I guess. But
it
yeah,
makes sense to a degree. So you were talking earlier about how like AFL does kind of experimentally supports it. And part of that's like the way AFL works is it provides you the argv. Like that's how it's sending you its input. So kind of just by its design, it doesn't really work with then you needing to pass the input off. So it kind of makes sense on why there's a little bit of workings. And also, if you're fuzzing like libraries or whatever, oftentimes you're more focused on what are my entry points into this library? What functions am I just going to call on that? And that's kind of easier to structure to give arguments to directly pass like a nice structure that's whatever. Just to do that and making the call, like you might do with like a libfuzzer setup. You set up the structure based off whatever input it's passing. Um, but I thought this was an interesting post just on that sense of doing the argv fuzzing. I don't think I've ever really needed to do this. Um, but it's good to keep in mind because it is generally going to be a really good entry point to a lot of different functionality when it's available. Something like libcurl and curl, a lot of entry points are like curl is going to be able to exercise most of libcurl. Um, so it kind of leaves you with with good access there. A lot of libraries don't have a binary that gives like a really nice interface, so not always going to be an option. But in this case, where it is, I think it makes a lot of sense to target or to go through this because that one entry point, as long as you can craft the right string going into it, and that is kind of a bigger difference there, is you're not going to be able to do as much when it comes to passing certain types of pointers or something like that. You can't really do that over a string. You're going to be somewhat limited in terms of your input to that degree, but it is going to be able to exercise a lot of functionality. You'll expect that it
your
should be able to
influence is going to be
hit.
pretty limited too, which is especially notable with these kinds of use after free type bugs. It like reallocation is going to be fairly difficult in these one shot command line style exploit payloads.
Yeah, so that's where it's going to pick up. I guess the way I'd kind of think about is argv fuzzing will be able to pick up, I guess, a wider breadth of like code, be able to get a lot more coverage over the code base than just going through a single function that you might be targeting, or more likely a set of functions that you'll try and target. But going through argv is going to give you a pretty good breadth of access, basically. So I don't know. It was interesting to kind of see them take this approach because, like I said, I don't think I've ever really need to do this. I don't think the thought has really come up for me. I can't think of too many times where I've actually had like access binary that really executed a ton of the functionality over argv. But in this case, like it does make sense, and there are other programs that do have like a binary to their library.
And I like Balika's message from chat. Even system curl plus params isn't safe anymore. Yeah. Argument injection on curl is now you're not safe anymore. um I also IHBR said Live Overflow did a very nice series on argv fuzzing sudo to show how it could find the sudo edit vulnerability. That's pretty cool. I'll have to check that out. For whatever reason, I haven't really kept up with Live Overflow's content as much. Like recently, I've just been busy with other stuff, I guess. But yeah, he does some really cool videos on the more like esoteric stuff like that. Like, yeah, he does some cool videos, so I'll have to check that out. I wasn't aware of that.
Yeah, I think I
Uh,
saw the series. I didn't realize. I guess it makes sense given what the was that Baron pseudo or whatever that bug was called. I saw that he was going for that. I guess it makes sense because that was through a command line thing. I just didn't realize that that's kind of what he was doing with that video. But yeah, or with that series. Sorry.
yeah. All right. Up next, we have a follow up to the Rustproofing Linux post series. We covered part 1 and 2 last week, the day of the when we were covering the episode, part 3 came out, and then the final part on shared memory came out after that. So we figured we'd do some quick coverage of the follow up posts, because we thought the first two were kind of interesting with the concepts they were exploring. Z, I'll let you get into this one.
Yeah, and again, kind of the whole series was taking a look at porting over old C code from the Linux kernel into Rust and vulnerabilities that could still exist through there. I did find these last two posts to be, I guess, a little bit more disappointing. Mostly because they show how effective Rust is at preventing some of these vulnerabilities, as it tends to be the case. The third post here is integer overflows, where it's inserting the runtime checks. Effectively, it's actually pretty hard to write kind of normalish looking Rust code that is actually going to be vulnerable. Because even when maybe does overflow, the array checks will pick it up, for example. Where's the first post here? There we go. First post, or sorry, fourth post, I guess technically. I have these kind of in weird order. On the second post, they end up looking at shared memory. They use kind of a double fetch as like their baseline vulnerability, which general practice for a lot of things like ioctls, where they use an ioctl here in this case, is going to be to copy from user and then parse. That way you just don't do the double fetching at all. But if you were to go and set up the shared memory, like it is an option. They admit that this is a bit contrived. Usually, if you're going to see the shared memory, it's going to be later on, but you may still see shared memory because it is a more effective way of sharing data without going through the whole copy process. So it can happen. But they end up showing the code here with the Vuln ioctl doing a double fetch vulnerability, so it reads the shared buffer index 0 and just checks the size. If the size is okay, it does the copy. But of course, the size can, because this is a shared buffer, the size can be swapped out from underneath it. After or between these checks, you basically have a little race window where you can change the value, and it does a larger mem copy than it should. When it comes to porting that over to Rust, the code, they show how you could do the same thing in the code. So ideally, you would probably want to use like the page object, or like using kind of the layers of abstraction it already provides. So it provides something that kind of gives you the page concept. You have to do unsafe because you're dealing with pointers, all that. Well, I guess you go to raw pointers in another example, but you'll notice it kind of just does like the unsafe read if size less than unsafe read size again. It really makes it a lot more obvious that something's going wrong here. Take a look at that C code. It's just if buffer 0 less than size, and then it uses the value immediately. Kind of easy to overlook the fact there is a little race window there where that value can change. Whereas in Rust, it's kind of obvious, like, you wouldn't write this code. I can't imagine many people would write this out, grabbing the size variable, and then not use it after checking it. Like, it's very obviously not how you would naturally write this code. They do make it a little bit more similar when they look at just using raw pointers instead of going through the whole page system. And it definitely blends in a little bit more. You'll notice how it just takes the unsafe there and grabs it a little bit later. The interesting problem here is that the Rust compiler will notice, hey, you're reading the same thing twice back to back here. It'll implicitly just create the variable and not even do the double read on it. You have to mark it specifically as volatile, so you have to jump through these hoops to make it go, or to make it do something insecure. So yeah, on the whole, like in terms of the Vuln research aspect, kind of disappointed here, but also kind of neat to see what Rust is doing and how it takes some of these code patterns that might normally be vulnerable and makes them feel quite a bit more obvious, or just catches them, as was the case with the int overflow stuff.
Yeah, the lack of convenience with accessing direct memory is what like really stands in the way here of being able to port these bugs over into Rust without noticing it. But yeah, another thing I want to mention is that shared memory, part of why I guess these look a bit more obvious too is the way shared memory is being used here. Like, obviously, it's a very contrived example, but it's happening in like ioctl, and it's getting it and using it right away. Um, Typically, when you do see shared memory, which isn't very common for what it's worth, um, it'll be like a good bit more. There'll be a lot more complexity around it. Typically, the only place you'll really see shared memory from a device driver is when you're trying to talk to a real like hardware device. So you see it in like GPUs and stuff like that, uh, or maybe like hardware acceleration or whatever. But like you don't like a lot of drivers don't expose that. So maybe in those more complicated situations, it's more viable for these types of bugs to spring up. But yeah, in a case like this where it is doing like just the one thing, like uh it would be pretty impossible to port over. But there might be some cases where it could happen. That said, the types of drivers that would be using shared memory are probably like the last ones that would be getting ported into Rust anyway, because they're the ones that would be the most like doing the most hardware abstraction, a lot of low level communication stuff. So yeah, so there's some like things to keep in mind there, but overall it's a pretty cool series of posts. It's talking about something we like to talk about a lot with Rust and memory safety. But yeah, with shared memory in this kind of situation, it's just Rust kind of shows how it can provide some uh like security in depth with just how difficult they make it to do that direct memory read in a way that's dangerous.
Yeah, and I really appreciate the fact they have laid these things out just through the series of posts, just taking a look at it again. It's good information to have, to be able to reference to see, how it's all laying out. And yeah, in this case, oh no, with the first couple posts, I was a little bit excited that they might be showing more about how Rust can go wrong. But, these last two are really very much about how Rust is a better option, and it is, for a lot of these use cases. Like, I'm not going to say let's all rewrite the kernel in Rust right now, like everything, but it has security benefits. I think that's reason. I think it's reasonable to say that that is undeniable.
Yeah. So Synactive last week put out a pretty complicated exploit chain. Well, it's a relatively simple bug, but they rolled their own custom TCP stack in the exploit, which is pretty insane. I believe this is coming out of Pwn to Own. This was a bug that targeted Western Digital, My Cloud Home NAS, which was one of the targets in Pwn to Own Austin. So that's kind of where it came out of. But yeah, I'll let Z get into the technical details of this one.
Yeah, and this one, yeah, like you said, there was a little bit of complexity around the TCP stack aspect. But on a whole, like the bug itself wasn't that difficult. Actually, I'll see if I can bring up the specific vulnerable code here. The core vulnerability, so the way this generally works and the way the NAS is working here is it runs Netatalk, open source implementation of the Apple filing protocol. Uh, as you might guess, it's used to share files. Makes sense for a NAS. And the way that works is it uses the data stream interface protocol, so DSI. And I'll be making reference here to this DSI structure. Effectively, DSI structure is kind of the whole management thing. For any connection, DSI structure contains all of the buffers: receive buffer, command buffer. Well, command buffer is the receive buffer. Reply buffer is actually one of the important things it has here. Data is used for reply. One of the other things that it contains is a set of pointers that are used for the read ahead buffer. So it needs to peek if there's any data kind of available, but doesn't want to officially write it. It's going to peek on it, and it's going to use these buffers for it, which tracks about the buffer, and that has like start, end of current position versus like the actual end. Kind of keeping track of as it reads into there, keeping track of where it is, multiple pointers. And then coming in, you've got the DSI blocks. That's basically what like all the packs are coming in, issuing different commands, having a request ID, and they'll specify like the actual length, which is then followed up with payload of the length size. So the vulnerability, now that I've gone through all of that, when it gets it's just going to loop forever, reading commands in, and it's going to switch based off of those commands. In the default case, it does this write init and then flush, which seems to be the case where it's just trying to flush. So write init is taking all of that data in the read ahead buffer. It's just going to take that and write that into the DSI data, passes in the buffer length, and then flushes it all out. So it's basically just taking the data, getting rid of it at this point. Well, sending it out, but getting rid of it for our purposes. The problem is the DSI write init function. It takes in this nice buff len, so it should be doing bounds checking, right? Well, no. It takes it in and it just doesn't use it. So you have a potential issue here. It will do the mem move. So data size is attacker control. This is all coming off the network. It'll only copy as much as as much information is basically available in that read ahead buffer. Also taking a min with that with data size, but effectively you have a potential overflow here because it's just not doing the actual bound check to make sure buff is the right size. It'll make sure it doesn't overread the read ahead buffer, but it's not checking the actual buff. And normally this isn't a huge issue because the read ahead buffer is only going to read about 8 kilobytes at a time, whereas this data buffer is 64 kilobytes. So you can really exploit this in a lot of cases, and that's where their custom TCP stack comes in, where some of the complexity of this exploit comes in. Because what they've taken is you have this, but you can't get enough data into that read-ahead buffer under normal circumstances. But they did find an exception, and that exception was during periods of network congestion, specifically if it gets blocked on a write. It's going to jump into the DSI peak function, and it's going to read more data if there is more data available on the network buffer. It's just going to go ahead and keep reading more in, hoping that if it clears that buffer, it'll be able to write again. And just so, it's doing something while it's blocked. So they have to trick the network stack into thinking, hey, you can't write anymore to this socket. We're not accepting any more packets from you. They have to trick it into that state. Once they're able to do that, then they're able to take it, get into the DSI peak, and have it read even more than the normal 8 kilobyte amount into that buffer, which then means when it lands in the write init, it will overflow. And just to be clear, the overflow here will end up corrupting basically all of this data after the because it's writing into DSI data, so it's basically has the potential to corrupt the tail end of this plus whatever's adjacent.
Yeah, that's kind of an important aspect, is that data buffer isn't like out of band; it's in line in the DSI like packet or whatever.
Yeah,
So any of those fields, which there are a lot of sensitive fields like buffer and start and stuff like that, there are like fair game for attacking.
Yeah, it makes it convenient for this attack because they don't have to do that heap grooming to try and end off with the right object nearby. They have some very juicy targets right nearby. So yeah, they're able to overflow that by tricking it into so what they end up doing to get it into this network state is they will turn around and they use Scapy to basically craft the custom packets to say like, hey, the TCP window, now this is 0, and then they tell their machine to stop like acking for new packets. They do that. They send a bunch of logout requests because that's not authenticated or anything. They send a bunch of those, and it effectively just leaves them in the case where it falls into that DSI peak route. They're in there getting a lot more data into that buffer, send a unknown command, and it goes and overflows DSI. So they can now corrupt that with pretty much as much data as they want. It is a very nicely controlled thing. Data they control, plus they overflow just as much as they want to overflow. So when it comes to the actual exploitation, one of the first things they take advantage of was the for an info leak, because there was ASLR on here. They simply take advantage of fact that there's kind of a replay cache. So if you send the same command twice, rather than processing the same thing twice, it'll just send back like the old or already known information for it. And in doing so, it doesn't overwrite the data length. So when they use their corruption, they corrupt the data length value. And then when they end up going to the replay path, it doesn't reset that value to what the proper size is. So when it replays it, it'll send back more information than they want. Effectively, you can think of it as just corrupting a size to give it a larger value. And then reading out more data. So they're able to read a bunch of data off the heap. Specifically, they find these hash t objects sitting on the heap. Most of the time, it was within access if they gave it, like, if they requested leak be like 2 megabytes. Most of the time, this will be on the heap. They could read kind of those pointers. Those pointers happen to be valuable to give them like the function pointers. They can get the slide or get like the offset of the main binary. So their info leak was effectively just corrupting a size, so they get a larger reply than expected. For their write primitive, this is where having that nice DSI object and having everything nearby, they were able to just, target these pointers at the end of it, saying, because that is user data that is being written into the read-ahead buffer, it's coming from the user, they have complete control, and now after one corruption run, they're able to point that anywhere in memory they want. So once they know how much is being read, once they're able to corrupt that, so they, or not how, sorry, using the leak, they know where everything is in memory, or at least the offset for what they care about. Now they can corrupt it second time and go for these pointers, overwriting them with a known address. So that gives them like just their write whatever where, or their arbitrary write. Lastly, for command execution, fairly straightforward. On the commands, when they would come in, it would just use a table, effectively look up the entry in a table. So they can enter their own function call, or their own function pointer, into that table. And from that table, what they were able to do is there was this AFP run command, which is an existing function in the application. And it would run shell commands, and you could even tell it to run the command as root. So very nice, win function for that. So they would overwrite one of the command entries with the pointer to AFP run and have it execute a root command for them, giving them a shell command, or well, they would overwrite, so it would give them a shell command. I think they just did a bind shell with that. Okay, I'm not seeing it here, so maybe I'm mistaken there, but oh yeah, they netcat bind shell there. You kind of see it at the end there. So effectively, they were able to eventually just get that, get code execution. Ultimately, a nice thing about this one, there was no ROP in here. There was no CFI violations. This would work if there was control flow integrity enabled. This was purely a data attack. Yeah, I mean, on a whole, nice exploit. A little bit of a pain to get through on the complexity of actually reaching that initial vulnerability. But after that, it felt like a lot of it was pretty straightforward. The corrupted size for an info leak, targeting a basically jump table style setup to get their code execution, and having the nice easy pointers in reach for their write what where.
I do just want to comment quickly on your CFI comment. I think it kind of depends. If you have the finer grained CFI, I think it would kill that attack strategy. I think you could still probably find a way to make it useful. Arbitrary write is your one of your end game primitives. It's kind of game over at that point anyway.
I mean,
but I think CFI could block their code exec trick.
The only play, well, because even fine grained CFI, usually that's just looking for okay, yeah, actually, I guess I can see some fine-grained CFI that would. Now that I'm thinking about it a bit more, fair shout. I'll walk that back. But it is a largely data-oriented attack. They are using an existing function, so anything that still lets you call arbitrary functions. But yeah, fine-grained CFI can still cut into that if it's targeting the function type. However, on that note, actually, as I'm talking through it a bit, a lot of the fine-grained CFI is looking at the type of the function rather than the specific address that it's okay to jump to. So if it's doing that, I'm going to imagine, I do not know for sure, that a lot of the command handlers, and I believe the this run command is like a normal handler that could, you know what, I might be wrong about that too. It might be a normal command handler elsewhere, perhaps. It seemed like it was, but I'm not entirely confident on that.
It
Um,
kind of depends. Like certain CFIs, it depends on how it's configured and what CFI is in play. Um, so yeah, it's
yeah,
something that's tricky to say without like putting it to the test. But
well, my thought
uh,
was even on a lot of fine grained, if it's going just on the type and like the signature of the function call, it would still match because it still looks like all the other function calls for these handlers. But it depends on that. So yeah, there is some complexity there. I'll walk it back a bit, but ultimately it is largely data-oriented attack, which is just fun to see. Like on a whole, I like seeing this over just, we did a ROP chain.
yeah. There was a question from chat about is CFI and CFG the same? CFG is basically just like Microsoft's terminology for CFI because Microsoft just likes to rename everything for no reason. It's effectively the same thing. Um, but CFI can come in like different forms. So you can have like your Clang based CFI, which is software. It has like the instrumentation put in by the compiler. But then you have something like Intel CET, which is a little bit stronger. I think there is support for it in Windows, but it's not like I don't think a lot of Intel CPUs support it yet. I think it's only like CPUs within the last year, maybe two, that have CET support because it's hardware. So, yeah, I mean, CFG and CFI are basically the same thing, but um, there are
CFG,
different implementations and how it works.
yeah, it basically says CFG is just the Windows specific implementation of
Yeah,
like their CFI. Oh, since you're mentioning like the CET stuff, I will say like GCC now builds by default with like that NBR instruction that's used for CFI on indirect jumps. So like it is being built in their default, even though a
a
lot
lot
of
of
systems
CPUs it'll
don't
be a NOP.
support it. Sorry?
Yeah, I was just gonna say a lot of CPUs it would be a NOP, but on
Yeah.
some of the newer ones it would work. Yeah,
Yeah, it's building with it, but yeah, most CPUs aren't supporting it, but it is getting built in there by default already. So that makes me think like we will see it as, assuming it gets more adoption on CPUs. It is still pretty new.
yeah. The final thing I wanted to say on this topic is I found it kind of funny that they were able to get such a clean exploit, particularly because of the struct layout of DSI. Typically, when you see these like auxiliary data buffers that user data is being put into, it's towards the end of the structure. Like they'll use the structure as a header, and then what follows is the data container. But having it in line like this and having sensitive pointers after it is just not a situation you see super often. But like in cases like this where you do see it, it's very nice for exploitation. So
Hey,
and
so
yeah, I guess on that note, where this is like an intra-object memory corruption, you were kind of talking about mitigations earlier, but even like memory tagging wouldn't catch this kind of corruption because it is within the same object. It's going to have the same tag.
yeah, I will say that is the reply buffer that's inline, not the user data buffer. The actual payload does come. That's part of that's out of band.
Yeah, sorry, that's fair. Yeah,
But they were
but
able
still,
to get control of that reply or of content in the reply buffer.
yeah, still though, generally those auxiliary buffers are towards the end. Um, but yeah, it's just it's kind of cool how that worked out for them here.
Yeah, definitely worked out nice for them.
All right, so we'll get into our last topic here, which is part 3 of the Masticore exploit chain for PS2 emulation on PS4 and PS5. last week we covered part 2, which was a pretty straightforward overflow vulnerability in Okage Shadow King. This final post is an out of bounds write in the PS2 emulator, which can be used to escape it and get full userland code execution, which was talked about a bit in CTurt's original post. Although this one goes a little bit more into the like detail on exploiting it, especially on the code exec side of things. So, as you'd expect, where there's emulation involved here, they have callbacks for doing memory reads and writes. And things like memory mapped.io have to be emulated as well. The registers that are relevant here for this bug were the cdvd s commands, particularly the scmd send and scmd status registers. So for those of you not familiar with like how mmio works, basically inside of the address space you have a device that maps some address as a register. So when the CPU goes to write there, instead of doing like your typical write to RAM or whatever, the device will intercept it and do whatever it wants to do. It's pretty critical to like lower level systems. So of course, when you're doing something like an emulator, it's a pretty critical part of it. So, and it's also easy to get wrong, and it's a great attack surface to look for problems. So yeah, the trouble here is when writing to the status register, the fake DVD device will update like this global status buffer with the written value, and it'll track the current position with this G status index like counter, which when the CMD status register is written to, you can basically use that to get a relative 1 byte write to escape the emulator because they just never check the status index. You can just keep incrementing it by sending lots of commands. Because yeah, there's only room for 16 entries in that buffer, and there's no bounds checking. So yeah, that relatively weaker primitive is used to smash the N status index global, which that's when the NCMD status register comes into play. That gives them the relative 1 byte write, which is enough to escape the emulator. Like that's a fairly powerful primitive, even though it's only 1 byte, because they can just keep exploiting that over and over again. Now, because you're escaping the emulator, mitigations are a factor, unlike the last post. So, like no execute, ASLR, etc. are in play. On PS5, execute only memory would be in play. The way they bypassed ASLR was quite neat. Because they basically did a partial overwrite of the function pointer for this O register read handlers, and they overwrote the last byte to give themselves a return gadget, which might not sound super useful, but it turns out that where this function pointer is followed, that the EAX register, which is used for return values in x86, it contains a pointer which can be used for defeating ASLR. From there, they figure out the memory layout, and it's fairly standard drop. Which they also use to leak the stack pointer for restoring stuff and whatnot later on. Because you can exploit this on PS4, execute only memory isn't super annoying. You can kind of get your gadgets through PS4 and then port it over to PS5 after the fact. If this didn't impact PS4, this would have been a lot more annoying to take advantage of because execute only memory would have been a problem here. So kind of a benefit of being able to target both systems here. There was some additional like complications when it came to exploiting this because you have to do like the save game signing. So there's a little bit involved there, but it's not really super relevant to the exploit, but that is towards the top if you're interested. But yeah, I mean, it's a pretty cool emulator escape. It's not too surprising that it was in the MMIO functionality for like the DVD stuff. Like I said, like MMIO is easy to get wrong, and where it's PS2 stuff, it's going to be older code. You can kind of expect to find those lower hanging fruit type issues. So yeah, cool exploit chain. Very useful as well for the same reasons I mentioned last week. It's kind of you can use this on any firmware basically. So yeah, cool vulnerability, cool exploit chain. There's a lot of background information here, and he goes pretty in depth on the ROP side of things. I'm mostly just going to skip over that because we usually don't cover like the ROP stuff, and there's nothing too insane going on there. But as always, link will be in the show notes if you're interested in the specific gadgets and whatnot that were used. But yeah, so that's the final part of. I believe it's the final part of the Masticore posts. So yeah, really good series overall. I would recommend checking it out for even if you're not interested in console stuff. There is some cool stuff there where there's an emulator involved and everything.
Yeah, kind of a cool chain, and just well done set of posts too.
For sure. All right, so that's all the topics that we have for this week. So Z, unless you have any last minute thoughts, we'll wrap it up.
Yeah, no shout outs.
All right, so thank you everyone who tuned in. If you want to catch past episodes, you can find them on Twitch and all of them on YouTube, Spotify, Apple Podcasts, and more on Anchor. If you want to join our Discord and follow us on Twitter, links for those are down below or in the chat as well. And with that said, we'll see you next week.